Hello, good morning, everyone. So my name is Markus Greiner, and as Hussein said, I'm in the physics department at Harvard, and we do research in my group on ultra-cold atoms. And so I want to give you a little bit of a journey in to what that means, ultra-cold, how cold are we, and why the heck do we want to be cold? There's a very good reason for that, as you'll see. We can do really exciting things that have to do with quantum computer and things like that. If we go really cold, and if you even go to the temperatures which are believed which are the coldest temperatures in the known universe, essentially. I will do some demonstrations. So every once in a while, I have to improvise a little bit here, and feel free to also ask questions during the talk or so, and we can try to make this a little bit interactive also. And yeah, let me think real quick. So I think Hussein will bring some nitrogen, right? Will you take care of that? And okay, let me check this real quick. Good. So, I will be talking about ultra-cold atoms. And so the field of ultra-cold atoms was actually pioneered by these gentlemen here, Eric Cornell, Carl Wieman, and Wolfgang Ketterle at MIT a long time ago. Bose and Einstein himself, they predicted that if you cool a gas to very, very low temperatures, that something pretty magic should happen. Namely that the atoms lose their identity, every atom is everywhere at the same time, kind of. I'll tell you more about what I mean by that in a minute. And so for centuries, this has remained a dream, kind of, and there were all kind of experiments trying to get into that direction, trying to achieve such a state. But it was pretty hard. But in 1995, this was achieved for the first time, and then a few years later already, they got a Nobel Prize for this achievement, because it was really, it made a pretty big splash. Ever since then, we have been able to use that kind of to study all kind of exciting things. And so let me, in particular, we can really use individual atoms as Lego pieces to build synthetic matter, essentially. And so that's what I want to tell you a little bit about this quantum Lego that we play. So I said that we are very cold, right? But just how cold are we? It's kind of funny. I actually have to go to a logarithmic scale here. You may know there is an absolute coldest temperature, right? So that's 0 Kelvin or minus 273 Celsius. And I apologize. I just realized, since I'm from Germany, I don't even know how many minus Fahrenheit that is. Does anyone know? How many minus Fahrenheit is absolute zero temperature? Do you know? That sounds about right. Yeah, 457 or so. Yeah. Okay. So it's really, really cold, right? But so the question is, but of course you can't be colder than that. So if you had a thermometer, it would just stop, right? At some point. That's zero, right? 0 Kelvin or minus 457 Fahrenheit or minus 273 Celsius. Okay. And okay, so the question is, how close can we come to zero? Right? So what fraction away will we be in the end? And so here I'm plotting this in terms of fraction. So here, this is room temperature, 300 Kelvin, 273 Fahrenheit, right? Normally, we will always stay, like everything you experience in everyday life, will stay very close to that temperature. And here, every line here is 10 times less temperature, 10 times closer to absolute zero temperature. And so nitrogen is not here. I will do that experiment in a minute. Let me just check, just to make sure it's not actually here. I guess he's getting it. Okay, so we'll try that in 1 minute. You may have seen liquid nitrogen. It's this liquid that's really cold, and I'll I will show you that in a minute. So this liquid nitrogen is just a little bit colder on this scale, right? But our experiments, they're all the way down here. So a tenth of 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 a tenth, nano Kelvin above absolute zero temperature. This is really incredibly cold because if you had a thermometer that reaches from here to the moon, let's say, okay, like imagine a really, really long thermometer, huge one, where the room temperature reading is at the moon and zero is here, okay, so it's that long, then on that thermometer we would only be the width of a hair away from absolute zero temperature. That's how cold we are, okay? And yeah, so I'll show you some demonstration in a minute about nitrogen. The funny thing is we are actually just as cold as these supercolliders are hot. Like temperature, if I have a gas of temperature, what is the temperature set by? Do you know? Who knows that? Like what determines if atoms flying around, if they're cold or hot? Do you have an idea?
How much they move around.
Exactly, how much they move around, right? So if they're really slow, then they're cold. And if they're really fast, then they are hot. And in a supercollider, they built the most complex machines on Earth to make them really, really fast, right? And then they're about here. So the speed of the atom corresponds to temperatures here. You normally say tera-electron volt. So this is as... but as much as they go to high speed and high temperatures and high energies, we go to low speeds, low energies. Okay. Yeah. I will tell you a bit more about the why in a minute. Oh, actually, there's some nitrogen coming. That's great. Let's explore that a little bit. So this is liquid nitrogen. Thank you. You want to give me the glass? Yeah, that's great. Then just put it down there. And I can just pour it, right?
Yeah, it's a rubber in it, but don't worry about it.
Right, I don't have to worry about that. So here's liquid nitrogen. This is nitrogen. Has anyone ever seen nitrogen or experienced nitrogen? Where's nitrogen? Yeah? Do you know? Mm-hmm. Where do we have nitrogen? Or who knows? I saw a hand back there. Do you know? It's an air. Exactly. Air is mostly nitrogen, right? But normally it's a gas. But if you make it very, very cold, it actually turns into a liquid. Just like water, if it's really hot, turns into steam, right? Well, with nitrogen, everything happens at a bit colder temperature. So it's gas normally. And if you make it much colder, then it's a liquid. Look at this. Ooh. So it's just a liquid, and what you also see is there's a lot of kind of, it looks like steam. This is actually because if the air suddenly gets so cold from the cold nitrogen, then it forms this kind of, so the steam is actually little water droplets, like mist forming in the air. So if I breathe in there, you can see that. But it's, yeah, it's really just, here I can show you some here. Whoop. See, it's really liquid, and then it turns. So the steam is not really the nitrogen. The steam is actually the moisture in the air, but the little, like you might have seen, little droplets when I poured it. Okay, so this is pretty cold. This is 77 Kelvin. So that's minus. Thank you. Minus 196 Celsius. And so much colder than what you would have in your fridge or so. Much, much colder. And Hussein, can you do me a favor? Can you go outside into the rain and pick me a flower? I see one out there. But don't tell the guardians. Okay, so I'll show you in a minute what happens if I put a flower in there, but let me show you one other thing. There are cool materials out there that are really quite special. And those are materials that that lose all their electrical resistance if they are being cooled down to very low temperatures. Not very, but to temperatures like this. And these are called superconductors, right? So current, like normally when current flows, it always dies down immediately, right? You need a battery to keep it running. In a superconductor, it doesn't die down. If you run, oh, beautiful, thank you. If you run current in a circle, it keeps running. It would never stop. And if current runs in a circle, right? Do you know what it does? It creates a magnetic field, just like a magnet. So it runs in a circle, runs, and it'll never stop. It creates the strongest magnetic fields on Earth. Right. And this is being used in various places. Let me show you such a superconductor. They also have other properties that are cool. For example, they float on a magnet here. Whoop. Look at this. Can you see how this one floats on this magnet here? There's nothing below. Can you see that? So it's just freely floating on a magnet. Pretty high up. Actually, it works pretty nice. Can I get one of your piece of paper? I want to just demonstrate that it actually... Thank you. Here, look, there's nothing underneath. Magic.
Where's the top? Is that also a magnet, the top?
So no, it's not a magnet, it's the superconductor.
Okay.
And what it does is it kind of holds on to these so-called flux lines of the magnets. It kind of entraps the magnetic field, and then it stays exactly at that position here. This just floats, right? Actually, this is a nice one. This stays cold very long. It only does it as long as it stays cold. Mm-hmm.
How much weight would the magnet support before it sinks down?
I would say try it out, except I think it's a bit cold to touch. So I can push it quite. Oh, I can actually push it quite a bit here. So this is a really good one. Wow. Yeah. So yeah, quite a bit. So maglev trains you could build based on this actually, and there were some prototypes being built, not really for commercial use, right? So the reason why this hasn't been done for commercial use is because it needs to be pretty cold, and that's pretty complicated, right? To have a train where you have a lot of this stuff inside, right? That wouldn't be so good. The funny thing is, there are two funny things about this. This was invented 30 years ago, roughly, I believe, yeah. Actually, when I was in high school, this was invented. And luckily, my teacher back then, he made those with us. That was so much fun. Like, you need the oven, kind of like the oven you need for pottery, and then you mix stuff together and bake it, and so we made them. And that was really cool. And then I asked my teacher, yeah, so how do they work? And he said, I don't know. The funny thing is, 30 years later, people don't really know, okay? I mean, they know all kind of theories, and a lot of people claim they kind of know, but they don't agree. So the fact is, so this is a great example for a material where quantum mechanics plays a very big role in understanding it. And that happens to be very hard. Like once you have quantum mechanics in a complex system, kind of, it becomes really hard to understand. And over the last 30 years, some of the smartest people try to crack that puzzle, kind of. And because if you really understand how this works, you may be able to design a better material. There's no reason why this shouldn't actually work at room temperature. I mean, it gets harder at higher and higher temperature, but look how beautiful this works here. So you could imagine, why not, it should be possible to make something like that also works at room temperature. There's absolutely no reason why it shouldn't, right? I mean, I don't know, but it's just a little bit harder. The same principles apply at room temperature. It's just, if everything shakes a bit more, it's harder to get it to that, right?
Did somebody try to do it at room temperature and claim it worked, and then it was...
It didn't, no, it did not, right? I mean, that was, exactly. I mean, you can make, by the way, you can make something float. If I take a sheet of graphene, like graphite, of ferrolithic graphite, it will actually float. But it will, because it's a paramagnet, but it will have much less it will be much less stiff. And then, of course, you can also build, if you just want floating, there are other ways to do it. You can use a feedback, like you measure constantly how high it is and regulate the current, but it won't just sit there and float by itself. Okay. Or, of course, this could be used for power lines without losing electricity, for small motors that have really, really strong, all kind of stuff like that, if you were to find such material. Okay. And so part of my research, actually, it's kind of is now to have a totally different approach to try to understand that. Not just calculate it, not just measure it, but build a model system completely independent of that actual material. See, now it's slowly warming up and coming down. Build a model system like, I call it quantum Lego. Like, we essentially use individual atoms now to, actually, just, since I got this nice flower now, we have to try that real quick here. So if I put a flower in here, oh, it's first it steams a lot, right? And wow. Yeah. That was crackling water. Still looks the same, but sorry. There's another one. You can see it freezes so hard that it becomes completely brittle. Whose is that? No. Is it mine? Yeah, I guess so. What does it say? No. Okay. Okay, good. So we try to build model system where, you know, like nobody can calculate it, nobody can just look closely enough at the material to understand how it works. So we do the other thing around. We just use our atoms as Lego pieces to build something and see if you can understand what's going on. Okay? And so I want to show you a little bit about that idea. So that's going to be ultimately the motivation why we want to be so cold. And okay, so cold. Let me turn this off here. Here's a so here's a picture of our apparatus. You can see in the center, this is a cloud of atoms. This is a vacuum chamber, and we can trap a cloud of atoms. And then you see, if I turn off the trapping, they fly apart pretty slowly. Do you know how fast do you usually move atoms in the air around us all the time? Any idea how fast, roughly, would the atoms around us move? Speed of light? No, probably not. Speed of, just not at all. Speed of sound? How about speed of sound? Would that make sense? Kind of makes sense, right? Because if the sound has to travel from here to here, well, the atoms can't travel all the way there. They would constantly bump into other atoms. But still, they have to kind of, in order to, you know, one bumps into one, then into the next, into the next, into the next. So roughly speed of sound. That's how fast atoms fly around all the time around us, okay? Here we have cooled them a lot already. And so you can see, here they're trapped. And now I turn them off and the cloud goes like this, like really slow, okay? This is already a million times slower. And the temperatures here are like microkelvin, like millions of a Kelvin or degree or Fahrenheit above absolute zero. It's very cold already. Right. And we do this by laser cooling. Ironically, laser beams, normally if you shine a laser, it heats up, right? But we can do cool tricks where we shine laser from all sides onto these atoms. And they only, you know, they kind of the photons of the laser, they push atoms and slow them down. Have you ever seen light exert a force on something? Have you ever seen light pushing something? That's actually, any idea?
Theoretically, like in solar sails.
Yes, you're absolutely right. Excellent. Solar sails, exactly. That happens in nature, actually. Do you know where that happens in nature? If you look up at the sky sometimes, if you see a comet tail. So if there's a comet and there's dust around it, the light from the sun the very small particles of the light from the sun over a long time accelerates them, and so then they finally form this kind of tail pointing away from the sun. And this could be used also as a solar sail, as you say, so you could, in principle, you could propel a spacecraft. You have to be a bit patient, but that would work if you have very thin foil or so. Right. And so the atoms are so small that they are pretty easily pushed around, and so a light beam can push them quite a bit. And so we can do it such that whenever they fly towards a laser, the light is Doppler shifted exactly to where the atom can absorb it, and then it slows down the atoms. Okay. So, but that's the first step. Unfortunately, that's by far not cold enough. The next step is kind of how you cool the coffee in your cup by blowing at it, meaning if you have atoms here and we constantly let the hottest one fly out and the others still bump into each other, then the rest gets colder and colder. Right? There are constantly always randomly some very hot ones created, they fly out and the rest gets colder and colder and colder. And so finally we form what's called a Bose-Einstein condensate. So the two steps. First is optical, and then the second one is by constantly removing the hottest ones.
How many atoms do you need to be able to achieve that process?
How many do I need? So we start out with about 1 billion atoms, and then in this cooling process, we actually lose about a factor of 1,000, okay? Because we have to get even 1 million times colder than what we started with after the light. So what you saw earlier in the movie, this was 1 billion atoms, then we do this, then we are down to 1 million atoms, right? In the end, we may only use 100 or so for the final experiment. It depends. Okay, now why do we need to be that cold? What's special there? You would think if the atoms are so slow, well, wouldn't they just be at standstill and everything would be boring, kind of? The cool thing is that the opposite is the case. At those cold temperatures or velocities, these atoms behave fully quantum mechanical. So what does that mean? They behave like a wave, okay? So it's a matter wave. Let's talk a minute about waves. What's a wave? Or where do you know waves? So you know, for example, you know waves if you throw rocks into water, right? Then, or at the beach, you constantly get waves. You know sound waves, right? Like if I'm talking, then the air in between wiggles back and forth, kind of, and the wave spreads out and reaches your ear, and you hear it. What other waves do you know? What other waves are there? You heard about any other waves? Electromagnetic waves, right? What do you want to say?
So, I was going to say electromagnetic.
Electromagnetic, exactly. So electromagnetic waves. What are examples for electromagnetic waves that we know?
There's also gravitational waves.
Oh, you're right. Actually, yes. So recently, for the first time, they found gravitational waves, right, where like how much you get attracted to something is being modulated like a wave, right? But do you know examples for electromagnetic wave? Light, exactly. So light is an electromagnetic wave which oscillates very, very fast already. Any other ideas for electromagnetic waves? Radio waves, exactly. Does anyone know how often does the wave... So radio wave is you have an emitter and it creates this wave and the radio picks it up and and plays you music essentially. That wave encode is turned on and off in the rhythm of the music essentially, roughly speaking. Do you know what frequency that is?
Isn't it about the length of a football field?
There are waves that have that length, yeah. Actually, it's about the length of the antenna that you use to receive. So if it's a radio, it's about the wavelength is about this long. If it's a cell phone, it's obviously smaller because cell phones don't have these long antennas anymore. These are microwaves, the same what you find inside a microwave. Okay, all kind of waves like that. And these are the radio waves, light, and so on. What I will be talking about are matter waves today. Okay, this is a wave describing matter, but it's not matter shaking back and forth. It's actually a wave that's the heart of quantum mechanics. Quantum mechanics says that if I want to know where a particle is, like an atom or electron or so, I really have to look at this. Light, right? Light is a wave, we said, but light is also a particle. Light is a photon, right? A stream of photons. And so you can kind of make a connection that you say that this electromagnetic wave kind of tells you where you will find the photons. The same applies for atoms. Actually, atoms and photons are amazingly similar in many ways. A lot of the experiments we do, you could also do with photons, kind of. And this quantum mechanical wave tells you where the atoms are. Okay. Normally, you don't see any effect of that because that wave is much, much smaller than the atom itself, so you don't care. Okay. But, let me get back to that. So one example of these matter waves is actually one of the example of these matter waves are, who knows what this is? Have you ever seen this in school?
Electron orbitals.
Right, these are electron orbitals. Why do they look like this? Why does an electron not just fly around an atom like a planet around the sun?
Because you can't determine where it is.
Mm-hmm. So these electrons at an atom, they are described by these quantum mechanical waves. It doesn't really look like a wave here, but that's because the wave gets attracted to the proton here. If it was free flying, the electron, then it would really be a wave. Right? This just looks a little bit different, but it's really just a wave. And it tells you, if you were to look, it tells you the probability to find the electron somewhere. But the cool thing is, before you look, you really have to assume that the electron is everywhere there at once. It's not just here or there, it's actually here and there. Okay? So, kind of weird, but actually, if you want to get to an intuition for that, luckily, when I was in high school, I was playing around a lot with lasers and interference, and if you do that, then you get used to kind of weird effects, because if you think of these light as photons, as light particles, then you really get used to these kind of ideas. Now, the special thing about waves, let me do this first. So this wave is describing where the electrons are, but normally it doesn't. But it also describes. I mean, everything is quantum mechanical if you look close enough. So an atom, if you just have an atom flying around here, it will actually be also described by a little wavelet. But it doesn't matter. At room temperature, you can just say this is just like billiard balls bouncing into each other. But if we cool it down more and more, you may have heard about Heisenberg Uncertainty. So if we know the velocity better and better, the position becomes more and more uncertain. Or what that means is that the atom will be described by a little wavelet. Or actually, this is nicer on this picture here, but a little wavelet like this. And the slower it gets, the larger this kind of wavy, fluffy thing gets. At some point, it gets larger than the atoms, if I cold enough. But at some point, it gets larger than the spacing between the atoms. And then every atom is this wavelet, and they start overlapping, and that's where it becomes interesting. Right? Atoms are waves, normally doesn't matter. If you're cold enough, it matters a lot. And ultimately, they overlap and form this and when they overlap, then they form this interesting quantum matter. Right? Now, you know that electrons, right? You said electrons are also these waves. Well, guess what? If you have a crystal or a superconductor, then these electrons are also these waves inside there, and they also overlap. And so and that's where it becomes really complicated. You cannot think of it as just electrons moving around. You have to quantum mechanically think about that. Even in metal or in semiconductors forming your computer, electrons are delocalized. Each electron is spread out over a very large volume in that material all the time. Right? Okay, but normally we can't really see it. That's the problem. And so, but let's talk about one property of waves that's really cool. What is the coolest property of a wave from a physicist's perspective, I guess? I'm not talking about surfing. Let's me see if I can do that. Can you see these colors here? Kind of, maybe for the ones who don't sit at the correct location. Let me try to activate the phone here. Do you know how to switch the projector to HDMI, Hussein? Oh, it's there? Okay. Cool. Wow, that works nicely. These cell phone cameras these days, it's crazy. They're pretty good. Look at that. This is just a picture of a soap bubble. And you see all these colors. And now we do a fresh one, maybe? Have you ever wondered why soap bubbles are colored? It's funny, when my kids were just born, I was outside in the front yard and played with soap bubbles. I could think, what a great excuse. Now I can play with that and study the colors without my neighbors thinking I'm weird. So, look at that. Do you see these colors? Why is it colored? It just, is the water actually colored? No, it's not. Any idea? Uh-huh.
The different layers of soap are reflecting the.
That's a good idea with refracting. If you refract, you can get different colors, like a rainbow or so, or like in a prism. It's not exactly refraction here, actually, interestingly. Did you want to say something? The same, yeah. The funny thing is, it's not refraction, actually. It's actually interference. What happens is, if you go from air to water, you get reflection. If you go from water to air again, you also get a reflection. So now you get two waves reflecting. And those two waves, they lie on top of each other. And the funny thing is, if two waves lie on top of each other, they can either add up or cancel out, depending on how they lie on top of each other. So if you just illuminate this with one color, it will, you would just see, depending on the thickness, if this is kind of exactly one wavelength thick, then it will be bright. If it's 1.5 wavelengths thick, it will be dark, or if the light gets delayed by that much. Turn this back to right. The idea is if two waves come together, one wave and the other one comes together the same way, then they add up. If one comes together and the other one opposite, then they actually eliminate each other. You can see that in water. If you experiment with water waves, you can see that. If you splash two water waves with your hand, and the two waves at the end of the bathtub come together in sync, then they will make an extra large wave. If you have them out of sync, they will cancel out. So normally we don't see that, because normally there's a lot of light from all kind of different directions and all kind of different wavelengths, and everything smears out. But here's a situation where the difference between the two waves is so small, because the soap film is so thin that you can actually see that in real. The soap bubble gets thinner and thinner and thinner, and the colors come because the different colors of light have a different wavelength, and so at different times they are actually adding up or canceling. So at one particular thickness, the red light just fits in exactly, but the blue has too long of a wavelength and doesn't fit in. And then at other thicknesses, it's the opposite. And ultimately, if it's thinner than the wavelength, then it just becomes transparent, and that's when it turns black, kind of, at the top. Right? And then there's no reflection anymore. And then at that point, it also pops. Observe the soap bubbles sometimes. It's really interesting. Like, you see how the colors become more and more intense, then they go entirely away once the soap film is thinner than the wavelength of light, and then they also tend to pop. Okay. Now, so interference is really important, and so if two waves add up, two waves can add up or cancel out. Well, the amazing thing is, but what if atoms now behave like waves? So that kind of means atom plus atom could be no atom, or atom plus atom, so atom plus atom could be more atom, or atom plus atom could be less atom. Okay, sounds very weird, but it actually works. But don't worry, the atoms will be somewhere, and also don't worry, in everyday life, this will absolutely not happen, I guarantee you. We have to spend millions of dollars to create situations where that happens, to build apparatuses complex enough. But this is the kind of, at the heart, this is what our atoms are doing. So the atoms, I told you we have these kind of atoms that we slow down until they start to behave quantum mechanically, like you can think of them as little wavelets, kind of. And then the next thing we can do is we can put them into a so-called optical lattice. The motivation is actually, the electrons in a crystal, they are trapped by they are trapped in this crystal, so they are kind of in this periodic potential landscape, kind of, I call it. Like they are floating around in this lattice. So I can now say, it actually really happened this way. Like in high school, I was playing a lot with hologram and interference, and then I was kind of thinking, well, we could maybe use that to also build kind of a crystal made out of light for our atoms. And then the atoms in that crystal of light move the same way as the electrons move in a real crystal. So that's the motivation. So we want to make a crystal of light with light beams. We use actually interfering laser beams, like laser beams are waves, and those waves can also cancel and add up, and they can form these kind of patterns then. And then we want to trap atoms there. Let me show you. I told you earlier, like light forces are very weak normally, so they only appear in like solar sails or comets. But you can actually, in biology, people are using actually laser beams to trap little particles. So this is what my colleague Ted Hensch in Munich, he made this movie here. He has little glass spheres floating in water, polystyrene spheres floating in water, and they're attracted to the light. If they're small enough and the light is strong enough, then you can attract things to light that way. Right? And in a minute here, a second beam, now I have this lattice kind of, and you see how these polystyrene spheres go into these kind of lattices and move around. Right? So now we want to be ambitious. Instead of having here, this was 94, that was the state of the art then. Now we don't want little polystyrene spheres, each of them having trillions of atoms. You want a single atom there. Is that possible? Yeah. And luckily, with this Bose-Einstein condensate, we have a nice way to load them, and then we use more or less the same kind of lattices, and then we try to load them in there. On top of that, what I wanted to do when I came here was to say, well, if you have them in there, wouldn't it be nice to actually see them? In such a lattice, they would be spaced by about the wavelength, half the wavelength, actually. So that's just okay enough spacing that you can see them in a microscope in principle. So what we did is we built a microscope to sketched here to see all the individual atoms in that lattice. Right? It looks, this is the heart of the microscope. This is a vacuum chamber. We need really, really good vacuum. Inside there's some special optics we build, and outside there's special optics we build. And I didn't bring a picture. These labs look crazy. You have to. There are hundreds, thousands of mirrors and lenses and lasers, and it's totally crazy. Maybe I can show you a picture later. Okay, and after a few years we got that to work. So we could see pictures like this. Look at that. Each of the bright dots is exactly one atom. If I zoom in, you can see that they actually are aligned on a grid. Okay. These atoms fluoresce light. If you're really careful, you can hold onto them very tightly and still scatter light, like fluorescent, and collect light from each of them. And so they're on a grid. The spacing between them is half a wavelength, half a micron, roughly. And we can take a picture of all the individual atoms in our egg crate, like an egg carton, kind of. Okay. And we can even look at the motion of atoms. Here you see individual atoms hopping around in this lattice. Okay. Of course, like once I watch these atoms, they behave completely normal, what you would expect from if you played with billiard balls or so, right? Just classical physics. They just move around in there and diffuse. Sometimes they hop left, sometimes they hop right, right? Actually, let me show you this real quick here. This playing, I think probably more the older generation may be inspired here. This is the first quantum computer game with individual atoms. And yeah, but Right. But the cool thing is if you don't watch them as they move, then they move quantum mechanically, and then we can really use them as quantum Legos. And so let me tell you next a little bit how they move in there. Okay. Right. So I want to use these atoms in the lattice now as a Lego brick to kind of build a material where these atoms move quantum mechanically, but I can also study it. I can look at each individual atoms. So if I put an atom, let's just say one atom into this lattice, I call it, into this kind of egg crate kind of thing. So classically, it couldn't actually move if it's cold because it doesn't have enough energy to make it over the hill. Quantum mechanically, a particle can actually go through the wall if the wall is small enough and if the particle is cold enough. And it will do that actually all the time. This is called tunneling. It's not as mysterious actually, because remember the particle is a wave, and so the wave just leaks a little bit into the neighboring sides. But this means the particle will move in that lattice. How is that kind of motion different from what we normally know? Let's look at an example actually. What would we normally get if we had a situation like where a particle randomly moves left or right? So if you do this, this is called a Galton board. I actually brought one. Let's try this out. Imagine the following situation. Imagine that at each of these pins, if I have a marble and I put it in here, at each of these pins, the atom will make a 50-50 decision and either go left or right. So let's see. There's marble run. So each one is randomly left or right. And then, what do you expect if it's random at each time? Intuitively, what would you expect? How, in the end, if I put many marbles in there, how would this work? Is it equally? Exactly. There are more paths that lead to the center, right? From here, if you start from here. Mm-hmm.
If you look at the probability for each, there's only like one path you can take for the side.
Mm-hmm. Exactly, yeah, very good. So it's much more likely to be in the center. Let's try it. That's right. Let me keep this in here. Maybe it seems to kind of have a slight tendency to one side, but maybe I didn't set it up quite right. It's probably slightly tilted. Okay, so thank you so much. Thank you. Okay, so it wasn't exactly the middle because this was tilted a little bit, it seems. So, but it's clear it's very unlikely to be on the outside, right? Actually, if you mathematicians a long time ago figured out that this is a very particular shape. It's called the Gaussian bell curve, exactly. So Gauss, you can calculate that, and you find that a lot in nature. Like if you ask about how much dirt is there on the street, away from the street, or so. I mean, a lot of things in nature look just like that. And okay. Now, but what if I do the same experiment with my atoms that are little waves? Instead of, the cool thing is they behave like a wave. They don't go either left or right. Believe it or not, they go left and right at the same time. And they keep doing that at each intersection. They go left and right at the same time. And then they are spread out. They are, as long as I don't watch them, or as long as I don't create the possibility to figure out where they went, you really have to assume that they go both ways and they are really left and right at the same time. Again, let me point out, luckily, don't believe anyone in whatever esoterics or what that tells you big things can be at many places at the same time. So absolutely not. For atoms, this only happens in these at these extreme conditions that are very complicated to achieve. So I showed you this. This is classically what happens, just random, right? You get this shape. If we do this quantum mechanically, so we place an atom there, I told you it's a wave, and what actually looks, if each time you had it 50-50 to go left and right, but it actually spreads out like a wave. It's kind of what you would expect, right? If you it looks a little bit as if you throw a stone into water, actually. It would kind of spread out this way. And the cool thing is that the atom is now really delocalized in over all of these positions. The strength of the wave tells you the probability to now find the atom at one of these positions. Okay, so if you actually then look where the atom is, the strength of this wave tells you how likely are you to find it at that position. And so it's really spread out like this. And if I shine light onto it to find out where it is, light, boop, then you'll find it at one position. It's going to be either here or here or here or here. And that's but the likelihood is given by the wave. So if I repeat this over and over again, and the likelihood is given by the wave, then I can count how often it went to the different positions, right? And then this pattern here should actually reflect the wave, right? If I keep repeating this, it would look like this, and this pattern would now reflect So this pattern would reflect the strength of this wave. And guess what? This looks completely different from what we had classically here, right? Like classically, you had this kind of Gaussian bell curve. Now we get something very different. It's much more likely to go to left and right, because that's where the different paths kind of interfere and add up. And here, let me show you a movie. When we actually do this in the experiment, here are individual rows, single atoms. We repeat the experiment over and over again. Of course, we cannot watch it while it moves, because then it wouldn't do that. It only does that if you don't create the ability to find out where it is. But then in the end, we find it at one position, and we write that down, and then we repeat the experiment over and over. And then we actually see, you don't really see it, but you kind of see this pattern here. This is the position, this is time, and you see how it spreads out. It has this ballistic motion. Looks very different from what you would expect classically. Okay. So that's how these particles move. They move like a wave, and that has very counterintuitive effects. Another counterintuitive effect here you saw, apparently this was slightly tilted, so they all went to one side. What happens with our single atoms on a lattice if you tilt it? Well, I would expect it to run downhill, right? If you actually do the calculation, you would, a theoretical physicist would tell you, no, it actually just does this pulsating motion. It spreads out and comes back to the same side. It doesn't at all go downhill because it can't get rid of its energy. It just spreads out, comes back, spreads out, comes back, and it goes downhill. Well, let's see. Our tilted lattice, what do our atoms do? Yes, in fact, they spread out. And then if I keep going again, they perfectly come back to the original side. And this you can really only understand if you, there's no classical way to understand why the atom should come back to that original same side after being, you really have to assume that before that it was spread out, because classically it would just run downhill here, okay? So that's very clear. With these single atoms, you can really beautifully look at our quantum Lego pieces, essentially, one by one. So this looks, the pattern that we generate versus time, and look like this. It spreads out and comes back and spreads out and comes back. This happens with electrons all the time in crystals, except people couldn't actually observe it directly because you cannot see the individual electrons kind of in a snapshot. But that happens all the time. And the nice thing is now with these experiments, we can directly see things like that. All right. Okay, so that was one part. Of course, Lego with one piece is no fun, so we need at least two pieces, which means that, for example, they interact the atoms repel each other, attract each other, things like that. And then we can study that in detail also. But what we really want is many pieces for Lego, right? And to create kind of cool, interesting states of matter. So I challenge you to build this. Right. But and the cool thing is then, look, this is our lattice again. These are our atoms moving in the lattice, right? And they are, each of the atoms is delocalized. Each of these atoms is now in many places at once, but at the same time, it will also feel all the other atoms. But since the other atoms are also at many places at once, it completely depends on, like everything depends on everything. It's completely crazy. Even with just a few particles, you actually cannot really calculate that anymore on a computer. That's the amazing thing. That's why people still don't know how these superconductors work. Right? But this is this is exactly the same that what happens in the actual crystal. Here you have the protons and the electrons move around, and they are just as quantum mechanically delocalized as our atoms. But here we can watch it. Here we can really see them one by one. And then we put them together, and we can do all kind of states. So for expert here, every atom is everywhere. Here now every atom has exactly found a lattice site, found a place, and it's exactly one per side. These atoms can also be little magnets. We can study that kind of magnetism, because now my atom is also a compass needle that points in all directions at once, essentially. That is in a superposition of pointing into different directions, okay? And we can study that. If you then do experiments, we can see the atoms, if they act like little compass needles, they spontaneously arrange in ways where they alternate, for example, up, down, up, down, up, down. Or have defects, and so you can really study a lot of this thing now, essentially with the quantum Lego, to build some kind of cool materials. It's not really a material; you couldn't hold it in your hand. It just exists in the vacuum chamber, but it has this close relationship to the actual metal or superconductor or so. Right? There are lots of different materials that people are eager to understand how they work. And there's a lot of progress in a lot of materials are pretty well understood, but there are many examples of more interesting quantum materials like the superconductors that are really not particularly well understood. Right, and so we can realize these simple models. For example, if you like spins, if you just have little compass needle atoms, kind of, the best supercomputer in the world can calculate 40 of them. So 40 they can calculate, but what if I want to do 300, which you saw pictures of 300 atoms or so, right? What if I want to do 300? It takes you would need about 2 to the 300. You need to store 2 to the 300 numbers in the computer. The problem is 2 to the 300, that's about as many protons there are in the universe, okay? So you could never build a computer of that size, fundamentally, okay? Kind of. The idea is, well, you may have heard about quantum computer, right? So why can we do things with just 50 atoms, 100 atoms? Why can we do things that the best supercomputer cannot calculate? It's very simple. These 50 atoms are only moving very simply. They, as you saw, they can move left, they can move right, and they feel each other. That's it. Simple system. But the best supercomputers cannot predict how they're going to move. Why is so that's essentially the power of quantum computers. That's why people want to do quantum computers, because quantum computers, even if it only had whatever 50 bits or so, could do things that supercomputers kind of can't do. Right? The problem is it's actually really hard to build a quantum computer, because you have to control the parts immensely well, and there are many people working on that. But it's really hard, and I think it's actually still going to take a little while. People think they can use it to factorize numbers, which is important for cryptography, or actually to hack codes. That's why the NSA is funding some of that research. But to me, the most interesting application for a quantum computer is actually to understand these materials, because then, yeah, that's most fun. The cool thing is you can take a shortcut here. we don't actually need this complete quantum computer. We can have and Feynman actually, he predicted that. You might have heard from him. He wrote a nice autobiography. He said that you can maybe build an analog computer, like not a computer that can do everything, but you can build a special purpose kind of analog computer that can, I mean, this is just a Lego model of some kind of wave motion. So this would be your Lego built analog computer, not for quantum problems, but for wave problems, right? In fact, like 50 years ago, people couldn't build powerful computers like you find in an iPhone or on a PC. They had to build these electronics analog circuits that could then help them to solve these differential equations that otherwise they couldn't solve, okay? And so this is kind of the same here. We can build an analog quantum computer where we put the system together, and even these 50 atoms, it's all analog. It's not digital numbers. It's really the atom here or here. But then it does things that no supercomputer can calculate. And actually, just as of a few weeks ago, we are now really studying very intensely this kind of system that is very much related to high-temperature superconductors, as I showed you. A year ago, roughly, our pictures were looking like this. We weren't quite cold enough. You see the individual atoms moving around. Then we got colder. You see that these atoms arranged nicely on a grid. And right, and then you can do all kind of studies with these atoms. And we have really, just as of 3 weeks ago or so, we have now really reached a regime which cannot be computed on the best computers. And so we're eager to push forward now to really, I mean, and with the microscope, we can just see what's going on locally. So that's just an immense tool for us going forward to understand this kind of quantum matter. Good. So I showed you from single how we go from single atoms to many atoms, and then we can build this complex matter in the lab, and also how you can understand that kind of as a quantum simulator or analog quantum computer. And I would also like to acknowledge all my students that are I hope having a lot of fun in the lab doing that, but it's also a lot of hard work to do these experiments, and I would like to acknowledge the funding also of various funding energies, because these agencies, because these experiments are not cheap. Okay, so and with that, I would like to invite you to ask more questions.
What is DARPA interested in?
They funded a project actually exactly on this. They want to, I mean, they want to constantly develop better materials, right? And so they funded a project to say, well, let's see how far you can push that with your experiments. Maybe you can build this, I mean, exactly this quantum analog computer they were funding. Mm-hmm.
Could you please explain a little further how one atom could be in two places at once? I'm trying to kind of understand that wave.
Mm-hmm. Right. So this wave is telling you where you would find the atom if you look. And this wave can then, a wave is never just at one point. A wave is always spread out somewhat, right? This is even true for atoms at room temperature. They are also described by this wave. But the thing is, at room temperature, the wavelength or the size of this wave packet is so tiny that it's completely irrelevant. It's much smaller than the atom. You can just forget about it. It's just, the atom is just a ball flying around, right? Well, for the electrons in orbitals, that's not the case. It's much lighter, so there it's much more fluffy. The electron is smeared out around the atom, right? By the way, you can understand the electron is not circling around the atom, then it would actually emit a radio wave all the time, right? So it cannot possibly. So instead of circling, the electron is actually just smeared out around the atom. Using that word loosely. But it just means this wave tells you where you would find the particle if you create the ability to find that out. Okay? Not if you look as a person, but if you create the ability to, in principle, find that out. Meaning, in air, other atoms bump into each other all the time, so they constantly measure each other where they are. So then it's also usually pretty irrelevant. But if you really isolate the system so perfectly, you can create the situation for an extended amount of time. This wave is spread out, and it can be spread out over micron, or a colleague of mine did experiments where you throw atoms up into a vacuum chamber, they come back. He can make an atom to be in a superposition of two spaces about 1 meter apart now. Right? This is actually used also for inertial sensing. So this is a great sensor for. They actually now build sensors like this that should go into submarines to see where they are, like inertial navigation, or measure gravity to find natural resources because this atom will be very sensitive to what's below, like if there is a more or less gravity below. Let's see. This is the. I mean, it's hard to wrap your mind around. If you want to get an intuition, just think about light. Right? Light is a wave on one hand. On the other hand, it's a photon. And if you make the light really dim so that you only have a single photon flying, like that you only have as much light corresponding to a single photon, you can experimentally easily show that even if the light is that dim, the wave goes, just like a water wave, goes through space, it spreads out, it comes back together again. And that single photon really must then be spread out. It cannot be either here or here. It has to be everywhere at once. So with light, you can explore that yourself. With matter, it's hard. We need these experiments to explore that. Right? And at the same time, this is not at all esoteric. It's very well understood. I mean, philosophically, at the end of the day, it's still kind of puzzling, because we are so used to the classical world that this surprises us, of course. But the great thing is we actually recently also experiments to really show that everything's fine with the classical world. Everything exactly turns to what you expect classically once you get to higher temperatures, higher densities, or bigger scales. Or this is all you have to work like microscopically. You have this quantum world, and you have to. Yeah, that's really the microscopic world. And once you go to macroscopic, it's all fine with your classical world. Mm-hmm.
Can you explain a bit more how you can simulate quantum computers analog with analog?
Yeah, so a digital computer, right, crunches numbers. There's numbers, and then bit by bit, there's operations on these, multiplication, division, and blah, blah, blah. And that way, for example, you can solve a problem. For example, how does a pendulum swing, right? You could calculate that, and then the computer spits out numbers at every moment, and you see a pendulum swings like that, right? That would be a digital computer. This computer can do all kind of stuff, but if you program it accordingly, it can tell you how this pendulum swings. If I now have an analog computer, then I would say, let's just build, for example, the perfect pendulum, right? And then I build the perfect pendulum and then I can see how it swings. I probably wouldn't call that a computer, it's just an experiment. But I could also build an electronic circuit that exactly encodes how this pendulum, that encodes the physical laws that I have figured out that affect the pendulum. I turn that into an electronic circuit, a different system, and then that spits out a voltage that goes back and forth corresponding to how the pendulum would swing. So this is not the pendulum, this is a this is an analog simulation. Right? These days you don't do that a whole lot because you have so powerful computers. But early on, like around Second World War, unfortunately, a lot of these things are how missiles would fly, or so. This was all encoded in electronics and mechanics and so on. Right, and so that's exactly what we do here. The actual material we want to understand is something like a high-temperature superconductor. You can't calculate it. So, and we don't have a quantum computer yet. So what we do is we build this model system, not with electronics, but with our atoms. And then we just let it do something and we observe it. And if we then observe the motion of holes or particles or magnets in there, then we learn about what also happens inside this superconductor. That's the idea. Mm-hmm. Sorry, that's it. The flower. So when I put the flower into the nitrogen, the water just froze. It got really hard. We can maybe play a little bit with that afterwards. And then once you crash it, it just shatters. The ice just breaks and now they're molten again. They will probably look a little bit stale, but now it's the same as if you had put the flower into the freezer. Mm-hmm. let's do some students first, and then any more? Yeah, sorry.
Well, you mentioned how you can use your technique by making like a sort of potential curve, kind of the light with the lasers hitting each other and interfering, and how you can basically simulate block oscillations with atoms rather than electrons. Would it be possible to like have lasers precise enough that rather than making sort of a perfect grid and testing block oscillations, you could make a slightly imperfect one to simulate like other types of crystals?
Yeah, absolutely. So what we actually do is, I told you back in high school I had fun playing with holograms, which I can highly recommend. There's some really nice hologram film out. And actually, this afternoon we'll make some holograms. It's just, you can never go beyond what you learn in high school, I think. But the idea is that we built something in this video projector up there. Is a little chip that has tons of little mirrors. Actually, yes, this is one with the mirrors. Each pixel is a little mirror that flips on and off very quickly. And then you see the picture. Each pixel here is a little tiny mechanical mirror inside on a chip. It's a MEMS device, okay? They turn on and off quickly. We use these chips as a hologram. And then we shine a laser on there, and then we can dial in arbitrary pattern. So we can really, instead of just having the simple lattice, the perfect lattice, we can create all kind of pattern, and we can just program it in what a video projector kind of can do, except we do it with lasers. So because we need actually much more light than you see on the screen, but we need that much more light focused onto a tiny volume, really high power lasers and stuff.
I know that to do nuclear fusion, not the kind we use today in the nuclear reactors, you need to focus lasers on a pellet and in all directions. But you said you also do that to cool something down.
Exactly.
How do you do that?
That's weird, right? So if you want to do nuclear fusion, you have these pulse lasers that all from all sides shine onto this little pellet, and then they create a shock wave and plasma and whatnot, and make it super, 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 super hot, kind of like the right side of my scale. And how comes if I do something similar, it gets super cold? So the main difference is that what we are directing the lasers on is not a kind of piece of junk, because if you have a piece of junk, I agree, really the only thing you can do is heat it up. If instead we have atoms flying around in a vacuum chamber already, or just randomly flying around, at first the light wouldn't do anything except if you hit the frequency of the laser is how quickly the light oscillates, and if it's not exactly the right frequency, then it wouldn't do anything to the atom. So that's a big difference. If you have a chunk of material, any light would get absorbed and heats up. With the atom, unless it's perfectly right, it doesn't do anything. If it's perfectly right, it would also just push the atom away and actually also heat it up. But if it's a little bit too slow, it doesn't do anything except if the atom flies towards the laser. And if then the atom flies towards the laser, you get this Doppler shift. Doppler shift is like if you hear a sound source coming at you, a car, the pitch gets higher, right? This also happens with light, of course, much less so. But it's so precise, kind of the atom senses the light so precisely that this little bit of shift is enough to then suddenly feel the laser, and then the photons from the laser kind of push the atoms and slow it down. Like if it's at rest, nothing happens. If it's moving to the left, this light will get absorbed and slows it down. If it moves to the right, then this light will get absorbed. The photons bounce it, and it's a drag force. We call it optical molasses also. It's kind of like honey. You know, it slows the atoms down. But you have to do it just right. If you don't do it just right, you're right. It would heat up, and also it wouldn't work with a chunk of material. It only works with these pristine atoms floating in a vacuum chamber.
Since you mentioned that you need to get it really precise, how do you, in the lab, how do you ensure everything is that stable? Like, what if somebody jumps, sneezes?
Yeah.
How do you control the experiment itself?
Yeah, I mean, it all starts with the HVAC system. The lab has to be precise, so half a Fahrenheit or something. And then, I mean, that's just the art of to me, there was a lot of fun to build these complex machines that have that kind of precision. It's lots of little things. So it's like you need the best lasers you can buy. You need the best vacuum you can make. You need the best of everything, essentially. And that defines the state of the art then, right? But it's actually pushing forward this field. It's quite amazing, actually.
How do you show that this is not an artifact of something happened? What if it's a big car or truck?
So there are lots of experiments we do understand, right? Like this motion I showed you of single atoms. So we have lots of ways to check that the system is behaving the way that we expect it to do. Right? And then we can go, from there we can then go the extra step where we don't understand it anymore. Yeah.
So what type of atoms? How do you pick what atom to?
Excellent question. To first order, it doesn't really matter. Our atoms are just little balls. Actually, there's one difference, fermions or bosons. I don't want to go there here, but it's fundamentally fermions or and bosons are, that's the main difference. It just depends on how many elementary particles they are made of. And bosons are always good friends. They want to be together. They want to be close to each other. Fermions, they cannot possibly. They're always, electrons are fermions. So if you want to study electrons, you want that. Cooper pairs in a superconductor are bosons. So this is pretty much the only, all the rest is just technical decisions. Right? So I showed you the Bose-Einstein condensate was done by Eric Cannell, Carl Wyman, and so on. Let me mention the fermions were done by Debbie Jin, who was a fantastic researcher in this field. Unfortunately, she passed away just very recently. I think she would have probably gotten a Nobel Prize very soon for these. So I had the great pleasure of working with her in Boulder, and she really pioneered these fermions and really started that field. So. Mm-hmm.
A few years ago, there was a mention that negative absolute temperature was achieved. Can you explain what is that?
Yes, you can. Negative temperature isn't so surprising if you have an isolated system. If you kind of positive low temperature is really, really the lowest possible energy. Negative temperature, low negative temperature is the highest possible energy. Now, if you have a system that's not well isolated, that doesn't make sense. If you have a lot of energy, it just it dissipates and makes everything else hot. But if it's really well isolated, and this is kind of what we can do in these experiments, then it's not so surprising that something can be really close to as high energy as possible, and it's completely symmetric. It doesn't matter if it's as cold as possible or as negative cold as possible, meaning the energies are as high as possible. Does it make kind of sense? Should probably saying, do we have to move on? Or what's the?
Yeah, if there are no more, excuse me.
There may be more questions, but I'm just asking for the schedule, so you have to.
During the break also. The lasers you use, what kind of power?
The lasers we use, what kind of power? Usually, luckily, we can use diode lasers, the kind of thing you find in CD players. But actually, recently, we moved into quite a few higher power lasers. Our strongest lasers now have 250 watt. You have to imagine a 60 watt light bulb only has about 3 watt of light. So we have as much light as 100 light bulbs in that laser. And that light is really focusing to a tiny, tiny spot. So like 100 light bulbs focused on the size of a hair. That's how strong these lasers are sometimes. So, and continuously, yeah. So there's a lot of that. Guys, let me also mention, I don't know, I've never really given a talk to students, but I want to really, I don't know, I want to motivate you to if you're curious about something, just go for it. Okay, there are so many, like, I was lucky enough to have had some exposure of this kind of stuff during school, which actually, funny enough, pretty much set the base for what I'm doing now, right? Trying to, the hologram stuff, which I had as a hobby to try to understand what my teacher couldn't answer me. So there's a lot of that. If you have a hobby in this direction, just do it. It's so much fun to turn your hobby into a profession, essentially. And also, don't I mean, I guess it's always time crunch and stuff, and I mean, I would say, you know, like, it's more important to develop, like, if you have a passion in science, you don't have to be perfect in every single grade. Okay, I wasn't perfect in every single grade because I had more fun focusing on the stuff that really interests me, and so I don't know, maybe just one thing to give you a path. If there's something that interests you, go for it. It's absolutely worth it and very rewarding. Yeah. Okay, so with that, thanks a lot. And if you have more questions, I'm still around.